Let's see, so, oops, oh, wait a minute, somehow it jumped down there. So let me just, maybe I'll just kind of try to encompass 3 sections together. Whoops. The 4, the 5, and the 4-1, the 4-2, and the 4-3 all together. But maybe what I'll do is I'll do this in slightly reverse fashion. So he's got this thing called Reynolds transport theorem. I'm not going to cover a lot of it, but at least to let you know what it is. He's got these terms, which he calls N. In the other book, they call them B or beta, but N is some type of something. So in the short term, we're going to call this the mass. Okay, so what you'll see by reading all this is that you can get the momentum, you can get the mass, you can get all sorts of stuff out of this. So what we'll do is just focus on oh man, it's going to rain in a few minutes. And we're just going to focus on the mass. Then what you realize is he's got this other term, a little nabla here, which is N divided by mass. So I'll just use that term and say that's going to be just 1. So if you're looking at the mass equations, these are the 2 values that you put in there. Usually, you don't write it MASS, you just write it M. So I'll just stick to that. So he's got this term, and basically this, which is the over the mass, and then the density times the volume, because the mass is equal to the density times the volume. So he's integrating over the entire volume. So he comes up with this property that's basically that. Okay, then he goes down, and he should have, okay, so here's the transport theorem. So what the transport theorem is, it's basically accounting for 2 or 3 things. And let me just use it in this way. So you got a bucket with a hole in it, and you start filling it with a garden hose. So in here comes something in here, water. So you focus yourself on that particular area or control volume or a volume of it, and you say inside there's a system. But notice what happens. He says the system, you're tracking the particles. So in essence, control volume is a location you fix your eyes on. How about focus on? And the system is you focus on particles traveling through the system. So you notice he drew these little dots. So you're accounting for every single particle. So what happens to you between these two is you have something that is exiting the system. Something is exiting the system and something that's coming in. So in fluids, we generally focus here. In a lot of the other areas, we focus on the system. So what we need to be able to do is take an equation that's built for the system and move it over to a new fixed reference where we watch things come through. So this is a typical case. You pour water into this bucket. Initially, it's kind of low. Because it's low, its flow rate is small out of here. And then over time, it fills up to a level in which the flow out of here is the same as the flow in here. So you get the mass in the bucket is a function of time, because the mass increases, well, the mass is, the density, times the volume in the bucket is changing. So you can write a differential equation, we could be able to do that. You may do it in the book, in which you can calculate basically the bucket rising. And what will happen is, it'll come to a steady state here, and that's where the mass flow exit is the same as the mass flow entry. But that's not the case to begin with. So, the equations, what do they look like? He goes through and ends up with them, and basically, I'll write the equations down using his terminology, and it's basically something like this. Equals to the time rate of change of integral over the control volume, and I'm writing them small, it's about the same size as that, times, he's going to use this term, so I'm going to use that term as well, d volume, plus the integral over the entire control surfaces of that same thing, and then rho, because the density has to be in there too. And depending on it, he may have v dot n dA, or he may have v dot dA, where a is the vector. This is the part where I'll have to scroll forward and see which notation he uses. So let me scroll forward. We'll look at those. Okay, wow, he breaks it. Okay, so there it is. Let me see if I can line it up. Okay. So you get the time rate change. Usually other books list this as a capital D, indicating that this is focused on the system. And I'll explain the difference. And then there's the, okay, so I forgot the density here. And rho, okay, so he says V, he uses the dA. So some books will write it like V dot N dA. Apparently this book writes it like V dot dA, indicating that the area has a direction associated with it, and we'll talk about that. So this is the local change in the volume, and this is what's called the convective change here, the part where the thing is going through or coming in. And so let me break this down to, and so the other book that I've seen does this with the system. And then what they'll do is they'll focus on the left-hand side. And they'll say this, d mass, d change in the system. Well, that's kind of defined as this. You're not going to create or remove mass. So this is basically the system part over here. And this is how you're focusing on fixing your eyes on a particular volume and letting things change in that volume or convecting through the volume. So what kind of implications does that have for mass flow? So I'm doing this kind of backwards, and let's see if he does a mass flow first. Applications. So here, let me just do this. I don't know, I did have paint up here a minute ago. Okay, I see it, but I can't get the mouse down there. There it is. So let me do it like this. So how does this, how does this effectively change or have an influence when you're talking about a mass flow? So, of course you know, here, let's do a simple problem first. And you know that m dot is equal to rho a v, which is equal to what they generally did in thermo, m dot in is equal to m dot out. And that's kind of convenient. So you just do rho a v in and rho a v out, assuming that things are going this way. Now let's see how this new connotation works. And then we'll show why we do it this way. So I'm going to use the other notation with the capital D, capital T, for a system is equal to this integral over the entire, throughout the entire control volume, rho this d volume, plus the integral over the control surface of rho v dot dA. Now, I'll go ahead and use his notation here. So we're going to apply this to this, and then what we're going to do first, we're going to say n equal 1 gives us the mass equation, which basically says d mass dt of a system is 0. That was determined earlier. In other words, if you have a system that is a fixed mass system, then the mass by definition doesn't change throughout time, and it gives you a 0. And then you do this part. And I think I may have to change markers because this one okay, now the little term here is 1, so you get rho d volume plus the integral over, this is throughout the entire control volume. This is throughout the control system of rho v dot dA. Now this is like the bucket. If the entire object is full of water, say, and air is not coming in and draining down, then the density and the volume are remaining fixed over time, and this term pretty much disappears. So if it disappears or equals 0, they claim it's steady state. And so then you're just looking at 0 is equal to this. Okay, so if you're looking at 0 is equal to that, well, a lot of people, let's be meticulous about it first. When we look at that, now that we see that, we have to identify the control volume, we have to identify the surface, and we have to identify the directions of the areas. So what we do is we look, say this is water coming through and going down a constriction. So what we're doing is we're identifying the entrance and the exit, and then I won't do much with the wall, but I'll say it's part of it as well. So this is part of it as well. And now, what is the area? So we've identified this is the control surface. Inside here's the control volume, but I don't care about it because I'm not integrating throughout it. It's steady state, so I don't care about it. I know the velocity is shooting out here, and I know the velocity is coming in here. But what about these D areas? Now, some books will write this like this: rho v dot n d area, where n is the normal. And so normal is imagine it's a porcupine. So everywhere there's a needle pointing out, and the needles all have a length of 1, but they're all perpendicular to the surface. In other words, I'll zoom in and we'll pay attention to this little region right here in a second. So if we zoom into that area, and we look at it, it's coming up like this, say, okay, let me redraw that. So say it's coming up kind of like this. So the normal comes out here, normal is coming out here, so it's perpendicular to a tangent, and the normal is coming out, say, right here. But there's no flow coming through the metal, so the velocity on the inside has to be, next to the metal, has to be like so. So let's just pick a particular location here. Here's your normal, so we'll just look at 1. Here's your velocity, and here's your normal. It just so happens that they're 90 degrees apart. If they weren't 90 degrees apart, water would be spewing out a little hole there, and that would make it an exit, or So the fact of the matter is, v dot n is equal to the magnitude of v magnitude of n, and the cosine of 90 degrees, because they're 90 degrees, meaning that there's no mass flow coming through the metal wall. And that's it. So now that you know that, that's why I kind of wanted to make it black, and the other is red. This one being black means there's nothing coming through it. But in fact, these little normal vectors pointing out are basically a little vector of d area. But some books like to put it that way, some books like to put it that way. I'm kind of talking like it's this way, which is okay. Now let's look at the entrance and the exit. Now, you could rewrite this equation in this way. I can sum it across the control surfaces of rho velocity average dot area, or some books again like to have that dot area to be dot n and area. And I'll do that for a minute. So let's look at the entrance. So this is the location of n. So the velocity is flying through here. Here's your velocity average. And here's your normal. So if you look at these two, V average, I'll just say that. V average dot n is equal to the magnitude of the velocity average, magnitude of n, which is actually 1, times the cosine of 180 degrees. What does that make it? That equals minus V average. If you're looking at the exit, here's your exit, here's your normal. They're going in the same direction, therefore this angle is 0. So guess what? When it's exit, it has a positive. When it's entering, it has a negative. So what you can do is you can come back and say, hey, wait a minute. I'll take 0 is equal to, I'll call it rho 1, V1, vector dot A1, make it as a vector, I can break it apart into normal, plus rho 2, V2 dot A2. This one is negative because it's entering. So what you have is 0 is equal to minus rho 1, A1, usually you do it rho 1, V1, A1, plus rho 2, V2, A2. And so it's the same thing. M dot n is equal to M dot out. So now why would you even want to introduce this if this is the case? Here's the reason. Let's say you want to know this. So now, okay, so if you're interested in this, you're doing mass conservation. If you're doing this, you're doing momentum conservation. So momentum, you've moved immediately, taken the same equation, you've moved from a mass conservation to a momentum conservation. And now what do? Well, guess what you do? You go in, I guess I can just start monkeying with the same thing. I go in and I'll say this. Now I'm looking at MV. Now this is a vector. And so therefore this should be a vector, therefore this should be a vector. But let's just look at it from a component viewpoint. Let's say I just want to know, because I really only have X here, I'm going to not worry about Y or Z. So I'm just going to, and this is the thing, Vx is equal to Vx. So I'm just going to look at the X component. So that means in here goes this, and in here goes this. So now what happens to this? Okay, now you've got a system which is, or which looks like, d m vx over dt. Is that no longer 0, or is that 0? As a matter of fact, no, it's not. If you look at, go back to dynamics, sum of the force in the x direction is equal to mass times acceleration in the x. But it's also equal to, and supposed to be written this way. So in dynamics, or initially they talk about it this way. This is really the equation, because the reason you don't talk about that one before you talk about that one is you can start talking about this before you even know what a derivative is. Now you know what a derivative is. This is the original equation. So in fact, what you do is you replace that with the sum of the forces in the x direction. And now what do? Well, it's steady state still, but I'm going to put this term in there. It has to be this, Vx, and there has to be a new term, Vx. And so you go up here, it's no longer this. Now, you got a new term. I'll move the row over a little bit. So I have a row, Vx, I have a row, Vx, and I have a row, Vx, and now what can I do? First of all, I can't do that anymore, so I can do this. I can do Vx1 and Vx2, Vx2, and minus V, minus Vx1, but it's no longer equal to 0. It's equal to the sum of the forces in the x direction. So just like that, instead of m dot in equal m dot out, and remembering that, and that's okay, suddenly we know how much do you have to hold this thing back, because the velocity is shooting out really fast here, it's coming in really slow, so it's like a fire hose. And if you set your fire hose out and watch, it'll flop around like crazy unless you hold it. So you hold it, how much force do you have? Well, let's just make up numbers. We'll say, we'll do it so that it's in SI, because then I can multiply it times that pretty easy. So those are my densities, they don't change. And I'll say V1 is equal to 1, and I'll say V2 is equal to 5. So that'll tell you right off that, okay, row 1, V1, A1 is equal to row 2, V2, A2, but these are equal. This is 1, that is 5. So I'm going to make area 1 equal 5 and area 2 equal 1. So I'm going to say area 1 is equal to 5. Area 2 is equal to 1. V1 is equal to 5. V2, I'm sorry, what did I say? V2 is equal to 5. V1 is equal to 1. V2 is equal to 5. So therefore, this times this equal to that times that. Suddenly, I can just instantly figure out the force required. The x component coming in is the entire velocity, so it's Vx. I'm going to put it in right here. So I'm going to say that is 1. This is 1,000. That's still 1. Area 2 was 5. This is still 1,000. Velocity 2, it got faster. Area 2, it's kind of smaller. And then velocity 2, I wrote that as a 2. Why did I do that? It's supposed to be a 5. So what do you got? 5,000 with a minus plus 25,000. And so the force required to hold it at this point is 20,000. And since I'm in SCI, it has to be Newton. So just like that, you move from mass continuity into momentum continuity, this is why you're doing this. This is why you're tracking the normals. This is why you're doing Reynolds transport. This applies no matter what. No matter what what it is. If it's counting marbles, if it's counting temperature, if it's counting anything. This case, the most useful case is the continuity. The second, well, I don't know. They're both about equal. Momentum has to be satisfied. These two are satisfied no matter what. Momentum, there's never been a case where momentum is not satisfied, nor mass continuity, except nuclear reactions, which actually, that binds itself from the mass to the energy, which actually you can put energy in here as well. And I think he does that in the next chapter, I think. Maybe it's in this chapter. There's the mass conservation. Oh, wait a minute. Reynolds transport. Oh, it is in the next chapter. Oh, well, okay. Okay, maybe it's right there. Let's just see if he uses it right there. Does he use it right there? System equation. Okay, no, maybe he doesn't use it right there. Oh, maybe. Okay, there you go. He's starting to use it right there. This DEDT, this is the system version of it, and he uses Reynolds transport. Okay, yeah, he says he's using Reynolds transport, where the little bitty n, or now, is the e, the little, oh, okay, I can't get rid of that, little e, which gets stuck in there, and it gets stuck in there. Then he goes up, oh, he says it's steady state. Then he takes the little e, and you get that, the kinetic, potential, and then that U, the internal energy. Then you go through, oh, he also, okay, he does the work, which is the pressure times that, and he should back out. Okay, so he ends up putting in the pressure over the density, up, and that U gets combined with the P over density, or in thermos, it's PV, and it becomes H, the enthalpy, which is not there yet. Is not there yet. And maybe he doesn't put it in here. Oh yeah, there, wait. No, he doesn't put it in there. Okay, never mind. He doesn't put it in here. Oh, here it finally shows up. H is equal to U plus, in the thermo it was PV, but here it's P over density, which density is 1 over the specific volume. So in fact, this Reynolds transport propagates itself through every bit of fluids there is. So let's look at, okay, so I'm in the wrong chapter, but I'll go back and we'll look at some problems. Now, the one thing he does too is he does this, and I skipped over that chapter, but now I'm going to, or that section, but I'm going to go back to it. And that is this: if you had a piece of pipe, and then you had, say, a parabolic equation that was the flow rate, then your V average, some average bulk, whatever, you could say control surface of the V dot, well, okay, I should say, it's kind of implied. So here's your area. You basically go across, in this case you would go in polar coordinates, and you would sweep out, but you wouldn't have to if it was in like a long thin plate. You just integrate that out. So, and of course, you have to do this. But let me go back to that section and we'll look at that. That was back here. So what I skipped over, okay. Okay, so we'll look here. So volumetric flow rate. Okay, so it's true. It is called Q. The volume flow rate is the velocity times the area, which actually this becomes, Q, which is cubic feet per second, cubic feet per minute, something like that. So what you're doing is you're integrating over the area the velocity. So it might have a profile. It could have a weird profile. It could say you had velocity profile that looked like this. Say the pipe came around a bend here, and the flow looked weird. It didn't line up, and so you integrate it. Well, you integrate it. If the mass flow back here, has a nice profile, the same amount of mass has to cross these two boundaries if the density remains fixed. So he's just telling you have to integrate across this to get the average. And that's generally what a lot of people are. So here he's showing he does very good with the graphics. I think they have a good artistic team. So here's a pipe, has like a parabolic profile. So it's like a three-dimensional parabola. And so you're basically looking at the velocity and you're integrating it over that area. So you're actually getting the volume of this little funny shape right here. Because, you think about it, you're integrating the area across this, and you're integrating at that point, you're integrating the velocity poking out to here. So you're getting the volume of this shape. And then, let's see, he doesn't really say anything new there. He does talk about the normals here. The D area has a normal coming out of it. And the volumetric flow rate is the volume times the area. So, the velocity times the area. So in other words, if you've got, if you've got feet per second, and this is like feet squared, then you get cubic feet per second, and that's used a lot. CFM or cubic feet per minute is used maybe more often. So here's a duct coming out of a house or some sort of building, maybe a cooking thing or something, I don't know. So if you want to know the average velocity, what do? You divide by the area. You get the flow rate, the volumetric flow rate divided by the area. And then he says mass flow. Okay, it's rho v dot A. So he starts with that. Then important points. So these problems are just a bunch of integrations, and usually the integration's fairly straightforward. So like here's one in which he's got an equation that looks like, well, first of all, where is his equation? Okay, the volume is determined by equation 4.1. Where is 4.1? Okay, that's great. That's correct, but he okay, wait a minute. I got stuck here. Oh, okay. One-dimensional flow. Oh, okay, here's the thing. Okay, here's the problem statement. The velocity is written like this. So there is his function of the velocity. So you have to integrate velocity d area. Well, d area is 2 pi r dr, and you put in the equation, you integrate it out. So that's all you're doing through some of these. And then he talks about finite control volumes. So I should have mentioned that, and I did. But here he's talking about a location you're sort of staring at and letting mass flow out and in it, or in and out of it. So control volume, and this is a moving control volume, but even if it's moving, momentum has to be satisfied, and continuity, And that's pretty much it. So I think what we'll do, maybe, I don't know, may let us go here in a minute, and then we'll come back and work several problems in I don't know, what does fundamental problems look like? Okay, so water flows in, there you go. Comes out of a triangle, goes into a circle, some equation. So we'll do a few of those. What's the difference between those and the actual problems? Probably not much. That's not much. Yeah, they're all kind of the same. Okay, now here's where you're getting to the point. Okay. 50 meters from stream reach point B. Assume the boat doesn't move. Okay. So I don't know what he's got there. Oh, rain falls. So we'll do some of these, and then what we really want to do is we want to move in to when does he ask us? Oh, fluid moment. That's weird. Okay, so all right. So chapter 4 comes up. Introduce Reynolds transport. You leap over it and you do energy, and then you leap back to momentum. So I guess I'll follow that sequence. But to me, momentum needs to be right here, and then, or work and energy maybe needs to be before 4. So it needs to be, anyway, I can cover them all relatively quick. And so what I'll do is I'll work problems from 4 and then 6, and then we'll go back to 5. Anyway, we'll call it good. It hadn't rained yet, but I got a notice that says it's about to. But I'm thinking it may have made a mistake there because it said it was supposed to start at 12:20. Maybe it's starting somewhere at 12:20, but not here.